Hello, welcome to our series on impulse manufacturing. I'm Glenn Dane. I'm a professor in the Department of Materials Science and Engineering at Ohio State. And this is a new format we're trying out where we'll have short inspirational movies. We'll have all the details, papers, theses, and all that over on the right. And this one's not going to get into very much depth. We just want to give a general overview of what we do. In our group are really to make the world a better place. We all know that CO2 is rising rapidly. At places like Mauna Loa, we've gone in my lifetime from about 320 parts per million up over 400 parts per million. And a lot of this is because we use energy, and energy use comes in a few different places. Big ones include the energy that's used in making stuff, and that includes making steel, making cars, welding, all those kinds of operations. Then the other one is really in transportation. If we can make lighter, more fuel-efficient cars, we can end up saving energy that way. I think that the way you solve both of these, or a big part of this problem, is actually through innovative manufacturing processes, and that's what we hope to offer, and that's what we're doing at my group here at Ohio State. The kinds of operations we're doing, this is really a big greatest hits montage. That the whole point of this video series is to go through this and talk about these operations, what can be done, how it can be done. And we got into this back in the 1990s. We found that formability could be enhanced. Others have used this for conformal joining. This actually flies in Boeing 777 and other aircraft. We can do collision welding. We'll talk about that in some detail. We can do precision embossing, including down to nanoscale and microscale, where you can emboss on optical diffraction gratings. We can do punchless cutting. We can control shape. We can take a die and form the metal, even high strength metal, right to the shape of that die. That's important. We can do some hemming operations, flanging operations. We can change metallurgical structure. And very importantly, the equipment that is used to do this is actually very light, very agile. It takes a while to understand what we're doing, how we're doing it, why we're doing it. And that's part of the point of this whole video series. So here's what we do at Ohio State. We've been doing electromagnetic forming and electrohydraulic forming for some time now. And it's a tried and true technique. It's really a staple for us. I'm trying to underline, not scratch out. We've also done some work with high-speed presses, not quite as much, but the things that are really special to us we've got a new vaporizing actuator technique that we'll tell you about in this set of videos that I think is very potentially useful. And we're also doing some very interesting work with laser-driven flyers. This builds upon what's been done in laser shock peening and laser shock processing, but uses it to take a flyer and make it fly at very high speed. If things fly at very high speed, some really interesting things can happen. This is an example where we've got 5 thousandths thick aluminum that's bonded to copper, and the aluminum, using this laser method, flies at about 1 kilometer per second, very high speeds. And then what you can do is when that strikes, the middle part strikes normal, but around the ring you get a ring-shaped region that bonds where there's an oblique collision at fairly high speed. This is that area here around the outside, and you can see the collision was enough that we're causing some spalling in the copper. If you look closer into here, you see the structure look like this. It looks very wavy. This is the copper on the bottom, the aluminum up top, but you get a real collision weld there with materials that normally don't like to weld to one another. If you zoom way in close, you can see that there's some very interesting metallurgical structure that happens there. So there's a real hierarchy of length scales in these kinds of welds, which is very interesting. And we'll talk about this in some more detail in the set of lectures. But what I want to do here is emphasize a little bit why we do this. And one of the things we're emphasizing, and we'll emphasize this, there's a whole bunch of new operations that are possible with this. And then also very, very important is the equipment is really light and very agile. We can develop tens of tons, up to say about 1,000 tons of pressure, but it only lasts for a few thousandths or millionths of a second, really, maybe 10 or 20 millionths of a second. We have high pressure, and if you've got a very high pressure for a very short time, just the inertia of fixtures can actually hold things together largely, and then bolts keep things from flying apart. So we can do work that requires really hundreds of tons with very light systems where we use electricity that comes out, either develops an electromagnetic pressure or vaporizes a foil. And so we can do work with small systems like this rather than with really big presses and really big dies, and that gives us some really big advantages with respect to agility. Things like make parts like this part, which is sort of like a prototype fuel cell bipolar plate or heat exchanger plate, where we can do forming, cut holes in, surface harden, all in one go, and that's really very interesting, very exciting, and it's done with very light equipment. So we see this as being an important piece of technology for agile manufacture. So again, just to give a little more detail, these are the kinds of things that are exciting to metallurgists like myself. These are structures that we can get by solid-state collision welding of multiple materials together. Turns out we can bond titanium to steel. We get even better interface properties if we can put an intermediate material between them, such as copper. We get these beautiful structures sometimes, and we can weld things that aren't usually weldable, and this is all happening again by very high speed collisions and sort of oblique collisions as well. And again, this series will go through this. What we're doing here is we've got a whole bunch of things we can do. We can enhance formability, we can do conformal joining, impact welding, embossing, cutting, precision shape control, hemming and flanging, and we've got this suite of high-speed impulse processes that are used. Explosives have been out there a long time. Electromagnetics has been out there since the 1960s. Brand new techniques to Ohio State are really using the vaporizing actuator in particular, and laser impulse. There are very few other places doing it, but there are a few others that look at this. So that's basically the big picture of what we do. That's what this site is going to be about. And you'll see that we have light, flexible equipment, we have shock hardening, we have some very interesting diagnostics you'll hear about. We can measure constitutive behavior, hear something about that. And that's what this is all about. Before telling you any more about the site, I think it's appropriate to acknowledge those that make it possible. And it's really the talent, creativity, and hard work of students and collaborators. This is a group taken a little while ago. Many of these folks are still with me today. Most senior people in the group, Anupam Vivek, Jeff Tabor, and Jason Johnson. Anupam and Jeff primarily run the group, and with happy guidance from me. And then we also have some sponsors, particularly generous. Recent sponsors include the Alcoa Foundation, Sandia National Labs, and the U.S. Department of Energy. So the way the site will work is we'll have some motivational, hopefully entertaining presentations, all given in the style and words of the authors of the work. So you'll hear all kinds of different things. And then hopefully off on the side here, we will have links to papers, theses, and really detailed work off there. And we think altogether this will make a very compelling and fun way to learn about this technology. Look forward to hearing from you. If you have any questions, please feel free to contact me, Glenn Dane. My name and contact numbers, contact information is on the page, or anybody else in my group, and we hope this is a useful resource to the manufacturing community at large. Have fun, enjoy the site, take care.